this video, we will talk about numerical methods and why they are important. So what is numerical methods? Numerical methods are mathematical techniques used to find approximate solutions to complex problems. These problems include high-degree equations or nonlinear functions that are difficult or sometimes impossible to solve using exact formulas. In many real-life situations, especially in science and architecture, problems are not simple. They may involve irregular shapes, large amounts of data, or conditions that are not ideal. Because of this, solving them manually or using traditional methods becomes very hard or even impossible. This is why numerical methods are very important. Instead of finding exact answers, they provide solutions that are close enough and still very useful in real-world applications. These methods also allow us to solve problems faster and more efficiently. Overall, numerical methods help us model and solve complex systems that cannot be handled easily using exact analytical solutions. For the first method, we will talk about the bisection method. The bisection method is one of the simplest numerical techniques used to find the root or zero of a nonlinear function. It is also called the interval halving method because it repeatedly divides an interval into two parts to locate the root. For this method to work, two conditions must be satisfied. First, the function must be continuous within the interval. Second, the values at the endpoints must have opposite signs, meaning f of a multiplied by f of b is less than 0. This ensures that a root exists between the 2 points. The idea is simple. We take the midpoint of the interval and check its value. Then, we choose the subinterval where the sign change occurs. This process is repeated until we get a value close enough to the actual root. For the step-by-step method, first is to choose an interval a and b where the function changes sign. Next is to compute the midpoint using the formula c equals a plus b divided by 2. Then evaluate the function at c. Next is to determine the new interval. If f of a times f of c is less than 0, the root is between a and c. Otherwise, the root is between c and b. Then, repeat the process until the desired accuracy or error is achieved. So for the formula of the number of iterations, we have n is greater than or equal to log times b minus a minus log times error over log times 2. For the error, we have e sub a is equals to b minus a over 2. For example, given the function f of x equals cosine of x minus x in the interval from 0 to 1 and an error of 0.001. So, in solving for our number of iterations, we have obtained a value of 9.9658 and n is approximately equals to 10. For our f of a, cos 0 minus 0 is equals to 1, and for the f of b, cos 1 minus 1 is equals to negative 0.4597. So moving forward, for our table, we have for the iteration 1, a is equals to 0, b is equals to 1, c is equals to 0.5 based on our formula. F of c, we have 0.3776 And absolute error based on our formula is equals to 0.5. Now for the second iteration, a is equals to 0.5 since f of c times f of a is positive, then we will change a to c. b is equals to 1, c is equals to 0.75, f of c is equals to negative 0.183, and absolute error is equals to 0.25. So after solving for everything, as we can see in iteration 2, f of c times f of a is equals to negative, so we change b from c, and as we solve till iteration 10, as we can see, we have obtained an error less than the given error, which is the 0.001. So now we can have our final answer. Next, we move to systems of linear equations using naive Gaussian elimination. It's called naive because it eliminates variables without checking the size of the pivot elements or if they are zero. This method has two main stages, the forward elimination and the backward substitution. For the forward elimination, the goal here is to reduce the matrix to an upper triangular form. For the backward substitution, once we have our triangular matrix, we solve for the variables starting from the last one. For example, using the value from our mesh analysis, we have here, the first thing we need to do is to eliminate I1 from row 2. So we use R1 as the pivot row. The multiplier is m is equals to negative 1 over 2 is equals to negative 0.5. Then we have the formula R2 minus 0.5 R1 equals to negative 1 plus 0.5 equals to 0. So when we change this row, the entire row will also be affected. So 3 minus plus rather 0.5 equals to 2.5. Then negative 1 plus 0.5 times 0 equals to negative 1. Then 5 plus 0.5 times 1 is equals to 5.5. So we have now our new matrix. The next step will be we need to eliminate this. So our multiplier will be negative 1 over 2.5 equals to negative 0.4. Then our formula will be R3 minus 0.4 R2. 0.4 times 2.5 equals to 0. So the entire row will also be affected. So 2 plus 0.4 times negative 1 is equals to 1.6. Then 6 plus 0.4 times 5.5 equals to 8.2. Now for solving for our back substitution, first is I3. So 1.6 I3 equals to 8.2 I3 is equals to 5.125 MA. For I2, we have 2.5 I2 minus 1 I3 is equals to 5.5. We will now substitute I3. 2.5 I2 minus 1, 5.125 equals to 5.5. So I2 is equals to 4.25 milliamps. So solving for row 1, I1. So solving for I1, 2I1 minus I2 is equals to 1. We will now substitute I2. 2I1 is equals to 4.25 is equals to 1. I1 is equals to 2.625 MA. So this is now our final answer. In conclusion, numerical methods are essential tools in modern engineering, science, and architecture. They allow us to solve complex problems that cannot be handled using exact analytical methods. By providing accurate approximate solutions, they make it possible to analyze real-world systems efficiently. The bisection method helps us find roots of nonlinear equations, while the Naive-Gaussian elimination method helps solve systems of linear equations. These methods are powerful, practical, and widely used in many real-world applications.